Hello and welcome to this lecture where I will briefly introduce Elasticsearch. Elasticsearch is an open source search server that is built on Apache Lucene. It uses Lucene as the core search engine but provides many features that are not part of Lucene. For example, usage of Elasticsearch relies on a comprehensive REST API. Like Lucene, Elasticsearch is written in Java and is therefore cross-platform and will work on many different operating systems. Elasticsearch was designed to be scalable from the beginning, which means that it has a distributed architecture. It's designed to take data from any source and make it searchable. Like I mentioned before, communication with Elasticsearch is done through an HTTP REST API. For instance, consider the example where an employee is fetched by issuing an HTTP request using curl. We'll see plenty of examples of this in this course, so I'm not going to go into the details of this right now, but just know that requests usually follow this pattern that you see on this slide, where the ID is optional. The documents that are stored in Elasticsearch are JSON documents that are schemaless, much like NoSQL databases. This means that you don't have to define fields and their data types before adding data, like is the case for relational databases, for instance. Elasticsearch is open source, but is being developed by Elasticsearch BV, which is a company that provides commercial solutions related to the search engine. Elasticsearch is near real time, meaning that from the point in time that one adds, modifies, or deletes a document, the changes are propagated throughout the entire cluster within 1 or 2 seconds. For small clusters, the changes will practically be propagated faster. Because of this distributed and scalable architecture, changes are not immediately available, like in a relational database that runs on a single machine, for instance. Elasticsearch has gotten very popular and hyped in the past few years. Part of its success is because of how easy it is to use compared to its competitors such as Apache Solr, but also because of the comprehensive feature set. Within the enterprise, its success is also much due to the fact that it scales extremely well thanks to its distributed architecture. On this slide, I just wanted to show you that the hype is not without reason, because a lot of large organizations make use of Elasticsearch, as you can see on this list of prominent users. This was a quick introduction to Elasticsearch. Now that you have an overall idea of what Elasticsearch is, we'll be moving on to discussing the terminology within Elasticsearch that we will use throughout this course. Thank you for watching. Hello and welcome to this lecture, where I will be walking through the terminology that you should be familiar with when working with Elasticsearch. First, I will explain what is meant by Elasticsearch being a near real-time search engine, something that I briefly mentioned in the previous lecture. What this means is that at the time one makes a change to an index, this change is propagated throughout the Elasticsearch cluster within 1 second. This is unlike relational database systems that are hosted on a single machine where changes become instantly available. This slight delay is due to Elasticsearch's distributed architecture, which makes the search engine so scalable. In fact, for large clusters, a delay of 1 second is really impressive. Now I will explain what an Elasticsearch cluster is. A cluster is a collection of one or more nodes or servers. A cluster can consist of as many nodes as you want, making it extremely scalable. The collection of nodes contain all of the data in the cluster, and the cluster provides indexing and search capability across all of the nodes. In practice, this means that when performing searches, you don't need to worry about which particular node a given document is stored on. Clusters are identified by a unique name, which defaults to Elasticsearch. I briefly touched the concept of nodes on the previous slide, but let me elaborate a bit. A node is a single server that stores searchable data and is part of a cluster. If a cluster only contains one node, then this node stores all of the data. Otherwise, a node contains a subset of a cluster's data. Nodes participate in a cluster's indexing and search capabilities, meaning that when operations are performed on the cluster, nodes collaborate on completing requests. Just as with a cluster, nodes are also identified by names, the default being a random Marvel character. By default, a node will join a cluster named Elasticsearch unless configured otherwise. Starting a single node on a network will create a single node cluster named Elasticsearch by default. Another key concept in Elasticsearch is an index. An index is a collection of documents, which could be a product, an order, or something like that. These examples would be a type within an index. I will explain what a type is in just a moment. The easiest way to understand what an index is to think of it like a database within a relational database system. This might not always be true because it depends on how you design your cluster, but it's a good starting point nevertheless, and will hold true for most use cases. Indexes are also identified by names that you choose, and these names must be lowercased. The names are used when indexing, searching, updating, and deleting documents within indexes. You can define as many indexes as you want within a cluster depending on the scale of your project, but most people will have one or just a few. Within an index are types of documents. A type represents a class or category of similar documents, which could be a product or a user. A type consists of a name and a mapping, where the mapping does not need to be explicitly defined. You can think of a type being equivalent to a table within a relational database such as MySQL. An index can have one or more types, and each can have its own mapping, which I will discuss on the next slide. Because Lucene, which Elasticsearch is built on, has no concept of document types, this is stored within an underscore type field. What happens internally is that when searching for a specific type of document, Elasticsearch applies a filter on this field. A document type has a mapping that is similar to the schema of a table in a relational database. It describes the fields that a document of a given type may have along with the data types, such as string, integer, date, etc. Also included is information on how fields should be indexed and how they should be stored by Lucene. Thanks to dynamic mapping, it's optional to define a mapping before adding documents to an index. If no mapping is defined, it will be inferred automatically when a document is added based on its data. The next concept that I will explain is a document. A document is a basic unit of information that can be indexed. It consists of fields, which are key value pairs, where a value can be of various types, such as strings, dates, objects, etc. A document corresponds to an object in an object-oriented programming language, and a document type corresponds to a class. An example of a document could be a single user or a product. Documents are expressed as JSON objects, and you can store as many documents within an index as you want. Now that I have walked through a few concepts, let me complete the analogy to relational databases. Where an index corresponds to a database and a type corresponds to a table, a document can be thought of as being the equivalent of a row in a database table. The fields of a document correspond to columns, and a mapping corresponds to the schema for a table. I will now discuss a term called shards, which is also a term that exists within relational databases, for instance. Perhaps you have heard of the concept of sharding a database, but don't worry if you haven't. An index can be divided into multiple pieces, and each piece is called a shard. This is useful if an index contains more data than the hardware of a node can store. An example could be that an index contains 1 terabyte of data, but the node has a hard drive of only 500 gigabytes. A shard can then be created and stored on another node which has enough space for it. A shard is a fully functional and independent index and can be stored on any node within a cluster. The number of shards can be specified when creating an index, but it defaults to 5. Shards allow to scale horizontally by content volume, i.e. index space. Also, sharding allows to distribute and parallelize operations across shards, which increases the performance of a cluster. While shards improve the scalability and the content volume for indexes, replicas ensure high availability. A replica is a copy of a shard, which can take over in case a shard or a node fails. A replica never resides on the same node as the original shard, meaning that if a given node fails, the replica will be available on another node. Replicas also allows for scaling search volume, because replicas can handle search queries. By default, Elasticsearch adds 5 primary shards and 1 replica for each index, meaning that unless configured otherwise, there will be 1 replica for each primary shard, which is 5 in total. This was a walkthrough of the basic terminology that you will see while working with Elasticsearch. Thank you for watching and see you in the next lecture. Hello and welcome to this lecture. In this lecture, I'm going to show you how to add an index to our Elasticsearch cluster. To do this, I'll be using the Kibana plugin, Sense, which we installed in a previous lecture. So what I'll go ahead and do is to issue a put request. So I'll write put, which is the HTTP verb that I'll be using. I'll write /e-commerce because I want to create an e-commerce index, because I'm going to simulate creating a web shop in this course. Now, before I issue this request, I just want to mention that this command is translated into an HTTP request that uses the HTTP verb put. So while I'm using a relative URI, you would have to use a fully qualified URL when using curl or when connecting to Elasticsearch in an application. To demonstrate this, I will just click the wrench icon right here and click copy as curl. If I paste the result into my browser's address bar, like so, you will see what the corresponding curl request looks like, which is the request that Sense issues internally. Also note that if you copy a curl request into Sense, it will automatically format it into the Sense syntax, which is pretty useful. So let me just copy this. I'll go ahead and delete this at the left hand side and copy in the curl request. And as you can see, Sense automatically formats this to its own syntax. Now let's issue the request to create our index. I'll hit the green triangle here. The index has now been created. Let's confirm this by issuing another request. Using the _cats API, we can retrieve a lot of information about our cluster in a human-friendly format, i.e. not JSON. For now, we'll just make use of the indices command. So I'll say get /_cat/indices, and I'll add a v query parameter, which basically just says that the output should be verbose. Now don't worry too much about this syntax for now, especially the _cat part, because we'll get back to it in a future lecture. I'll just issue this request, and the result shows various information about the indexes in our cluster, such as the number of primary shards, replicas, documents, deleted documents, and so on. Note that the indexes have a yellow health tag to them. Yellow means that some replicas are not yet allocated. The reason this happens is that by default, Elasticsearch created 1 replica for the indexes. But since we only have 1 node running at the moment, that 1 replica cannot yet be allocated for high availability. until a later point in time when another node joins the cluster. Once an index's replica gets allocated onto a second node, the health status for that index will turn to green. It's also worth mentioning that one does not have to create an index before adding a document to it. By simply adding a document with a put request, Elasticsearch will take care of creating the index for us using default settings. While this is very convenient, adding an index in advance gives us more control up front. We have now added the first index to our Elasticsearch cluster, and that's all we set out to accomplish in this lecture. So thank you very much for watching, and I'll see you in the next lecture. Hello and welcome to this lecture, where I will show you how to delete an index. In fact, I'm going to delete the index that I created in the previous lecture and add it again later in the course. So I have the Sense plugin for Kibana opened, where I will issue the request needed to delete the index. So to delete an index, I'll use the HTTP verb delete, and I'll say /e-commerce, which is the name of our index. Let's just issue this request. So now our index should have been deleted. Let's ensure that the index was deleted correctly by listing all of the indexes within our cluster. As in the previous lecture, I'll make use of the _cat command here, /indices, and I'll make the output verbose. Let's issue this request. As you can see, we no longer have an index with the name of e-commerce. Thanks to the REST API that Elasticsearch exposes, it's really that easy to delete an index in Elasticsearch. That's all I wanted to show you in this lecture, so thanks for watching and see you in the next lecture. Hello and welcome to this lecture. In this lecture, I'm going to add a mapping to our e-commerce index. Now I previously removed this index. If I had not removed it, then I would have to do it now. The reason for this is that if you have data in an index, then you need to create a new index and add the data to it, because you cannot apply new mapping information to existing data. However, if the index has no data, then of course there's no need to remove the index first. So I'm going to add the index anew. So I'll use the put HTTP verb /e-commerce as we did before. Only this time I'm going to add mappings. So I'm going to add a property here named mappings. And in here I'm going to say product, which is the type that I would like to add to this index. And let's configure this type. And I'll give it some properties right here. The first one will be name. And within this object, I'm going to set the type to string. Next, I'll add a price property. The type will be double. As you can see, the IntelliSense of Sense is really helping me out here, so it's very convenient. Next, I'll add a description property. And let's set the type to string, which is the default that Sense suggests. I'll also add a status property, also with a type of string. And let's add quantity 2. Set the type to integer. And let's add categories. Now the type of this property is going to be nested, because I want to add objects within an array. And the reason for this is that it's very common for a category to have an ID and a name and other attributes perhaps. So I'm going to say properties again, which holds the properties of the nested objects. So each category object will have a name property. and this property will have a type of string. Now in here you could add other properties as well, but I'm just going to use name. In my particular case, I didn't need to add this as an object, but I'm just doing it just to demonstrate how to use nested objects. Let's go ahead and add one final property, which will be named tags, and it's going to contain the tags for a given product. And I'll set the type to string, even though this will actually be an array of strings. But since Elasticsearch will automatically detect arrays within JSON when adding or modifying a document, then I actually don't need to define it as an array. And in fact, Elasticsearch doesn't have an array type. And that's it. Let's go ahead and issue this request. Like so, and it seems like everything went well as expected. So it's really that easy to create an index with mapping in Elasticsearch. Thank you very much for watching, and I'll see you in the next lecture. Hello and welcome to this lecture, where I'll be adding a document to our index. I've opened up Sense, and I'll issue a put request. When adding a document to an index, it's optional if you want to supply an ID for the document. If the ID is omitted, then Elasticsearch will generate a random ID and then use it to index the document. In this case, you should use the post verb instead of put. In this example, however, I will supply the ID, so I will issue a put request and add the ID to the URL. So let's begin typing out this command. I'll write put / the name of our index, which is e-commerce, / product, which is the type of the document, / 1001 as the ID. And in here I will add the properties of the document. So I'll give the product a name. I'll say send framework 2 from beginner to professional, which is the name of one of my courses. I'll set the price to 30.00. I'll add a description. Let's say learn send framework 2 in just a few hours. Let me just make this a little bit wider. I'll set the status to active. The quantity will be 1, let's say. And here I'll add categories. And remember that this is an array of nested objects. So I'll add an object in here with a name property. I'll just set it to software. And that's the only category I will add. Let's also add some tags, which is going to be an array. Remember that I mapped this as a string, but Elasticsearch will automatically detect this array and convert it appropriately. So let's say send framework, and another tag could be ZF2. Let's add PHP, and lastly programming. I'll just go ahead and run this. And as you can see, it says successful 1 and created true. So the document has been added to the index and it's now searchable. Let's confirm this by opening up Kibana. So I'll navigate to localhost at port 5601. And now it's asking me to configure an index pattern. So I'll just remove this checkbox and I'll actually just write the name of my index in here. You could also put in an asterisk, but Right now I'm only interested in this index as it's the only one that I have. Click create and then go to this discover tab up here. And we should be able to find the document by searching for send framework in the search bar. And it seems like we found it. And as you can see, the document that we just added shows up, and the matching parts of the query are highlighted in yellow. We're going to get into more details of writing search queries in the next section, so for now I just wanted to show you that our document does indeed exist within the index. And I also wanted to show you that Kibana is quite convenient for performing quick searches while you're developing. So that's all for this lecture. Thank you very much for watching. Hello and welcome to this lecture. In this lecture, I'll show you how to easily replace a document within an index. In fact, the way to do this is identical to how you add a document to an index. Therefore, what you have to do is to issue a put request with the document as JSON. So I'm just going to be lazy and copy in the command needed to do this. I'll just change this to be a number. And as you might have noticed, I have changed the price to be 40 instead of 30 as it was before. So I'll just issue this request and everything went well. So Elasticsearch will replace any existing document with an ID of 1001 with the data that we specified. If no document already exists for that ID, it will be added. This means that you don't have to worry about whether or not the document already exists in the index, which saves you from having to perform a lookup and then update the document. Let's open up Kibana and verify that the price has been updated within our document. So I'll navigate to localhost at port 5601, hit enter, and make sure that I'm on the Discover tab. And I'll search for send framework to find our document, expand this, and as you can see the price is now 40 where it was 30 before, so our document has indeed been updated. So as you can see, replacing documents is extremely simple in Elasticsearch. And that's all for this lecture. I'll see you in the next one. Hello and welcome to this lecture. Now instead of replacing a document, oftentimes you'll want to update it with some new information. Instead of replacing our Send Framework 2 course product, in order to change the price, we can just, change the price. This means that I don't have to supply all of the fields again, but that I only have to pass in the fields that I want to update. We can do this by issuing a post request, as I will show you now. So I'll enter the post http verb /e-commerce /product /1001 and /_update, which is an endpoint for updating documents. And within the request body, I'll type in the property doc, and this doc property is going to contain key value pairs of fields that we would like to update and their corresponding new values. So I'll say price because I want to change the price, and I want to set it to 50. So this will change the price to 50 and leave the rest of the document's fields unchanged. So let's go ahead and issue this request, and I'll navigate to Kibana, go to the Discover tab, search for the product, and as you can see the price is now 50. So this is very convenient if you want to update just a few fields and you don't want to supply all of the other fields. So this is how you update specific fields within a document without supplying all of the fields and replacing the entire document. Thank you for watching and see you in the next lecture. Hello and welcome to this lecture. Now that we have added, replaced and updated a document, it's time to see how we can delete it. As you might have guessed, this can be done by using the delete HTTP verb. So let's go ahead and write delete slash the name of our index, which is e-commerce, slash the type, which is product, slash the ID of the document that we wish to delete, so 1001. I'll just issue this request, and now our document has been deleted. Now, by default, it's only possible to delete documents by ID. However, there is a plugin named Delete by Query, which lets you delete documents that match a given query. I won't get into that, but I just wanted you to know that it exists. So if you need this functionality, then you can go ahead and Google this plugin and install it into your Elasticsearch cluster. So that's all it takes to delete a document in Elasticsearch. Thank you very much for watching, and see you in the next lecture. Hello and welcome to this lecture. In the previous lectures, I have shown you how to add, replace, update and delete individual documents. In this lecture, I will show you how to perform these operations in batches. To do this, I will use something called the _bulk API. Performing operations in batches is very efficient because it limits the amount of network overhead. This is because when doing 20 updates, for instance, a batch operation would result in a single network round trip instead of 20. The _bulk API expects a single line with the action, i.e. create, update or delete, as well as metadata, followed by an optional line of the source for the action. The source document is optional because it's not needed for deletions. This can be repeated as many times as you like. It's important to note that the _bulk API uses new lines, that is, \n, to infer the semantics of a given line, so JSON cannot be formatted to look pretty and span over multiple lines. Also, the final line of data must end with a new line, character, being \n. Let's see an example of this and add two documents to our index. So I'm just going to paste in a request here and briefly explain it. As you can see, I'm issuing a post request to the e-commerce index into the product type and the _bulk API. The first line indicates the action and default is creating a document, and I'm supplying the ID of the document. The next line is related to the first line, and in this case it's the source document. So this is just a JSON object with the fields for the document. And then I have another action line followed by another source document. So I'll just go ahead and issue this request. As we can see in the results, both of our actions were successful. Let's just verify that the documents have been added by opening Kibana. So I'll open a new tab and navigate to Kibana. And I'll just search for peanuts, which is one of the products that I added, and see that the last product was indeed added. Let's go back to Sense. And next, let's try to make a bulk request with more than one kind of action. I will delete the product with an ID of 1, and I will update one of the products that I added just before. I will update the quantity of the book that I added from 12 to 11 to simulate that a copy was sold. So let me just copy in the query, like so. As you can see, I'm deleting the document with the ID of 1, updating the document with an ID of 1002, and here is the specification of what will be updated. This is exactly as you saw when we updated a document in a previous lecture. So I'll just issue this request, and everything seems to have worked. Now I'll just verify that the document with an ID of 1 was indeed deleted. So I'll say get/ecommerce/product/1, and let's see the result. And as you can see, Elasticsearch didn't find a matching document, so it was deleted correctly. Next, let me go back to Kibana, and I'll do a search for awesome to find the book that I updated and verify that the quantity is now 11. So let's see here. As you can see, the quantity is indeed 11 now. Now, before the end of this lecture, I just want to mention a few things. On the lines where you specify the action to be performed, it's also possible to include the name of the index and type of documents to use. In my case, this data was present in the URL, but if I add it as the _index and _type properties respectively, I don't have to specify this information in the URL. This is useful if a bulk request affects multiple indexes and/or types. If, however, the index/type are provided, they'll be used by default on bulk items that don't provide them explicitly. When issuing bulk requests, both the index and type are optional in the URL. As long as the information is available within the actions, you can do any of the following. So let me just copy in the examples. So in the first example here, you can see that we have the index name and type name in the URL. So we don't have to specify this information within each action. But below we are omitting the type, which means that we'll have to add this within each action. And in the last example, we're also omitting the index. So we'll also have to include that in our actions. Otherwise, Elasticsearch doesn't know which indexes or types to affect. In the next example, I will just leave out the index and type and specify it within the action. So in this example, I will just simulate that we have sold another copy of the book. So I'll reduce the quantity again. I'll just copy in the command, or rather the request. And as you can see, I'm posting to _bulk and I'm not specifying any name of indexes or types. But note that I'm doing this within the action itself by specifying the _index property and the _type property. And the rest of this we've seen before, so I'll just go ahead and run the query. And if I go into Kibana and search for awesome once again, you'll see that the quantity has now been reduced to 10. So the document has been updated exactly as with the previous approach. Another thing I want to mention is that all of the actions in a bulk request are executed sequentially and in order. If a single action fails for whatever reason, the remainder of the actions will still be processed and left unaffected. The response for a bulk request includes a status for each action that was executed in the same order that they were requested. This is useful for checking whether or not a specific action succeeded or failed. And that's all there is to bulk requests. You should use these whenever you need to modify a fair number of documents at the same time to improve performance. Thank you very much for watching. See you in the next lecture. Hello and welcome to this lecture, where I will briefly show you how to retrieve a document by its ID. I've actually shown you this before in another context, but I'll just briefly show it again. So I'll issue a GET request. I'll specify the name of the index as well as the type, followed by the ID of the document that I would like to retrieve. So let's go ahead and issue this request. And as you can see, the product in this case was found. So we have some metadata right here. The name of the index that the document belongs to, as well as its type and ID, and also its version. The found property just indicates that we have a match. The underscore source property here is just the document itself, so it's the JSON object that we added to Elasticsearch when we added the document. So that's all it takes to retrieve a document by its ID. Let me just briefly show you how the result looks if we try to retrieve a document that doesn't exist. In this case, you still have this metadata, specifically the index, type, and ID, but now the found property has been set to false, and there is no source document because the document was not found in the index. So, thank you very much for watching, and I'll see you in the next lecture. Hello, and welcome to this lecture. Before I will get into actually performing searches against my Elasticsearch cluster, I want to introduce the basic concepts of searching in Elasticsearch. In this presentation, I will talk about relevancy and scoring in Elasticsearch. I will also briefly introduce the two ways of searching, as well as the various types of queries. Elasticsearch calculates a score for each document that matches a given query and ranks the documents according to the score. The higher the score, the more relevant the document is to the search query. When searching, there are two different contexts where queries can be applied: query context and filter context. Queries within the query context answer the question, how well does the document match, assuming that it does match. Queries applied in the filter context, on the other hand, answer the question, does the document match? If a document does not match a filter, then it's disregarded and will not be part of the results. It's important to note that filters do not affect the scores of matching documents, but rather filters documents out that don't satisfy the requirements of the filters. Now I will briefly introduce the two ways of searching with Elasticsearch, namely by query string and using the query DSL. The first way that you can search using Elasticsearch is with query strings. This method uses only a URL to perform searches, and the search query is defined by using a query parameter. It's usually used for simple queries and ad hoc queries on the command line, but it also does support rather advanced queries. On this slide, you can see an example of how a query could look like. The URL specifies the endpoint of the Elasticsearch cluster and searches for documents of the product mapping type within the e-commerce index. The underscore search API is used to perform the search, and the search query is specified as a query parameter. All fields are searched by default. This HTTP GET request is all it takes to performing a search in Elasticsearch. The other way is using the so-called query DSL. With this approach, a query is defined in JSON within the request body of a request, rather than in the URL. The query DSL is more flexible and supports more features than the query string approach, and is therefore often used for more advanced queries. For more complex queries, the JSON can also be easier to read than a long query string. At the bottom of this slide, you can see a query that is similar to the one I showed you a moment ago. The only difference is that with this query, I explicitly defined which field I'm searching, but I could also specify the underscore all field if I wanted to. In this case, I'm searching for products that contain the term pasta in their names. As you can see, the Q parameter has been replaced with JSON in the request body. Now that I have introduced you to how you can perform searches with Elasticsearch, I will move on to talking about the various types or categories of queries. There are two main types of queries in Elasticsearch: the leaf and compound queries. Leaf queries look for particular values within particular fields. This could be pasta within a product's name field, as in the previous examples. These queries can be used by themselves without being part of a combined query, They can also be used within compound queries to construct more advanced queries. Compound queries are therefore queries that wrap leaf clauses or even other compound query clauses. They are used to combine multiple queries, usually using Boolean logic, and can be used to alter the behavior of queries. Full-text queries are used for running full-text queries, meaning looking for a term in potentially a lot of text. The examples in this lecture were all full-text searches. When adding documents or modifying values of documents, the values for full-text fields are analyzed. Depending on the analyzer that is used, this process can involve removing stop words, tokenizing words, and lowercasing the text. For searches to match, a field's analyzer is also applied to the query string before executing a search query. Term-level queries are used for matching exact values and are therefore usually used for structured data such as numbers and dates. An example could be finding persons born between year 1980 and 2000. Because term-level queries are used for exact matching, the search queries are not analyzed before being executed. Because performing joins in a distributed system is expensive in terms of performance, Elasticsearch offers two forms of joins that are designed to scale horizontally. The first is the nested query, which you may remember from when I talked about the nested data type. If a document contains a field of the type nested with an array of objects, then each of these objects can be queried as independent documents by using the nested query. Next are the has_child and has_parent queries, which are useful for parent-child relationships between two document types. The has_child query returns parent documents whose child documents match a given query, while the has_parent query returns child documents whose parent document matches a given query. So, the has_child query is used to add query clauses to child documents, whereas the has_parent query is used to add query clauses to parent documents. Last but not least are geoqueries. As you might recall, there are two data types for geofields, geopoint and geoshape. There are a number of geoqueries that use these fields to perform geographical searches, such as finding nearby points of interest based on GPS coordinates. There are quite a few of these queries, so I'm not going to go through them right now. That's all I wanted you to know before diving into searching, which also happens to be the most fun part. So, join me again in the next lecture, where I will show you how to search in Elasticsearch. Hello and welcome to this lecture. In this lecture, we'll take a look at searching through the use of query strings in the URI. The query string API is powerful and contains many features, so I'm just going to show you the basic and most important ways to use it. If you need a complete walkthrough of the query string API, then please refer to the documentation. Let's write a simple query to start with. I'll use the e-commerce index and search for documents with the product type. To perform searches, I'll use the _search API because I want to search by query string. Let's write a simple query to start with. I'll use the e-commerce index and search for documents with the product type. To perform searches, I'll use the _search API, and because I want to search by query string, I will add a q parameter. The value of this parameter is going to be our search string. For the first example, I just want to show you how you can match all of the documents of the product type within the index, which you can do by using an asterisk as a wildcard. This can be useful if you want to have an index of all the documents, for instance. So I'm just going to say q equals an asterisk. Let me go ahead and issue this request. As you can see, 1,000 documents are matched, which is the total number of documents in the index. I'll just take a moment to discuss the important parts of the result. Within the hits key that you can see over here on the right hand side, there are two meta properties about the results. The total property contains the number of matched results, while the max score property contains the highest score of all the matched documents. The nested hits property contains an array of matched documents. For each document, you can see the meta fields that we discussed in a previous lecture. Another important property is underscore score, which is a score indicating how well the document matched the search query. This number is based on complex mathematical calculations, and you don't need to know more about this for now. The underscore source property contains the matched document as the JSON that we added to the index when we added the document. Next, let's try to search for a specific value. For example, let's say pasta. So let's run this query. Now by default, the query string searches for all fields, unless one or more fields are specified in the query. In this example, we are therefore searching for the term pasta in any field within a document of the type product within the e-commerce index. So as you can see, we have a number of results where the product names include pasta. Like I said, we search for all the fields, but it just so happens that only the name field has a value of pasta, in my index at least. We can also specify which fields should contain the value. We can do this by adding the name of the field, followed by the colon, and then the value. So let's update the query. I'll say q equals name colon pasta, like so. This means that we're searching for pasta in the name field. With our test data, this gives the same result. But if I change the field's name to description, then you will see that we get no matches. So let's try this. Description. And like I said, no matches. Those were the very basics of searching with query strings in Elasticsearch. In the following lectures, I will talk about more features before I will move on to talking about the query DSL. Thanks for watching and happy searching. Hello and welcome to this lecture. Now that I've showed you how to search all or specific fields, let's take a look at how we can embed Boolean logic into the query string. I will search the name field as we did in the previous lecture, but this time I will add parentheses. So let me just begin to type this out. I'll issue a GET request to the e-commerce index as we've seen before, to the product type, and the underscore search API. And I'll add the query string. I'll search the name field, like I said, and I'll add some parentheses here. Within the parentheses, I will add the pasta term, like so, followed by a Boolean operator. In this example, I will use and I will add the term spaghetti afterwards. This query searches for products that contain both the term pasta and spaghetti in the name. So let me go ahead and issue this request. And as you can see in the results, we only get one result which contains both of the terms in the name. However, if I change the Boolean operator to OR, then you will see that I get more results, because either pasta or spaghetti has to be in the name, and we get a lot of matches because pasta is in a product's name. But as you can see, the product that has both of the terms in the query is ranked higher or scored higher. It's also possible to make more complex logic by simply adding more Boolean operators within the parentheses. Let's try another example where we include multiple fields. Say, for instance, that we want to find the active products that contain pasta or spaghetti in their name. So I'll just have to change the query a little bit. I'll add parentheses around what we had already, and I'll say and status is active. Let me go ahead and run this query. And as you can see, we no longer have the product with both pasta and spaghetti in the results anymore because that particular product had a status of inactive. So as you can see, this allows for quite powerful searches. You can also use Boolean operators within the query string itself for even more control. Prefixing a term with a plus sign means that the term must be present, while prefixing a term with a minus sign means that it must not be present. Any terms without a prefix in such a query are optional. This is similar to how you can do in Google search, for example. Let's take a look at a quick example. I'll say that the term pasta must be present and the term spaghetti must not be present. So let me just remove this query and write a new one. So I'll say name, colon, because I'm searching the name field, plus pasta and minus spaghetti. Let me go ahead and run this query. And if we scroll through the results, we see that the product named pasta-spaghetti is no longer returned because we said explicitly that we don't want results where the name field contains spaghetti. So this was a quick introduction to using Boolean logic with the query string. Thank you for watching and see you in the next lecture. Hello and welcome to this lecture where I will be talking about the phrase query when searching with query strings. By default, all terms are optional as long as at least one term matches. This is because the default Boolean operator is OR. We can see this if we search for pasta spaghetti. So let me go ahead and type out a search to our product type, the search API, and I'll say name colon pasta space spaghetti. And let's go ahead and issue this request. And as you can see, we even get results that don't have spaghetti in the name. But what if we wanted to search for a specific phrase? This can be done by enclosing the phrase within quotation mark. So let's add quotation marks to the query that we just executed. Like so. And I'll go ahead and issue the request again. Now we only get one result, which is the document that contains both pasta and spaghetti in its name and in that order. Just to demonstrate that the order matters, let's try to switch the terms within the phrase around. So I'll just go ahead and do that. Now I've switched them around and I'll run the query once again. As you can see, the product no longer matches because the ordering of the terms does not match. Let's just reverse the order again and go back to the previous search result. Like so. Notice that there's a hyphen in the product name as well. So why does this phrase match? The answer has to do with how Elasticsearch analyzes documents when they are added to an index or their values are modified. By default, the standard analyzer is used. So let's just check how this product name is analyzed. To do this, there's a convenient _analyze API, which returns the terms after the supplied value has been tokenized. I'll set the analyzer to standard and pass in the product name as the text to analyze. So I'll just write this out. Get/_analyze. And like I said, I'll set the analyzer to standard and text to pasta-spaghetti, which is the product name. So let's go ahead and issue this request. The result is a list of tokens, and as you can see, the hyphen was dropped during the tokenization process by the standard analyzer. And this is why our previous search query matched with a phrase that did not include the hyphen. So those were the basics of the phrase query. Thanks for watching and happy searching. Hello and welcome to this short lecture, where I will just mention a few things about the query string approach before I will move on to showing you how to search with the query DSL. Firstly, I want to mention that any special characters that you include in the query string must be escaped with a backslash. Special characters are any that have special meaning to Elasticsearch, such as parentheses, plus, minus, and equal signs, question marks, etc. Now, there are more features available to you if you are using the query string approach for your searches. We will get back to some of it in the following lectures, but if you have a use case that cannot be solved with what I walked through in the preceding lectures, then I encourage you to check out the documentation on query string searches. If that also doesn't help, then you can post in the course discussion and I'll do my best to help you. You should now have an overall understanding on how to perform searches with query strings in Elasticsearch. In the next lecture, we'll take a look at searching with the query DSL, which is the other way of searching in Elasticsearch. Until then, happy searching.